Right, so today we have a special machine learning seminar. Jose Bento, who is now at Boston College in computer science department, who used to do a postdoc at Disney Labs in Boston before there was at Stanford, a PhD. And he'll tell us about the new convergence rate of Nestorov's acceleration.
Thank you for coming. I know that there's a lot of competing talks, so I appreciate you guys being here. So I'm going to be talking about Nesterov's method and a new bound for it that we obtained by using some control theory. So this is a technique that is kind of fairly general, and it has been applied to a couple of algorithms. And so it is something that might be useful for you guys to know as well. Might be able to solve your own problems. Okay, so what is Nesterov's method? So let's assume that we want to minimize an unconstrained optimization problem. We know that in gradient descent, we just make small steps in the direction of the gradient. In Nesterov's method, we basically do kind of the same thing, but we have a momentum term. So we tend to keep going in the same direction that we're going as we move along. And this not only have a step size alpha, but now we have a parameter beta that controls this momentum term. And so why do we care about Nesterov's algorithm? Well, because in general it has a faster convergence rate. In fact, you can prove it has faster convergence rates than gradient descent if you properly tune both. So for example, for a very simple example of a quadratic function that has optimal solution x1 is equal to x2 is equal to 0. The best rate you can get from a gradient descent method is 1/3. If you optimally tune alpha, and the best rate you can get from Nesterov's scheme is smaller than 1/3 if you optimally tune alpha and beta. And what do I mean by rate? So by rate here, I mean if we want to look at the error and we want to get bounds, the error at an iteration t, and we want to look at bounds of the kind the error at t is bounded by some constant times tau to the t. Okay, so these will be the rate. Okay. And since the functions that we will be looking at are strongly convex, you can always bound things non-trivially with something like this. Okay, so the error always converges exponentially fast to 0. Okay, so just a quick recap on the family of functions that we're going to be working on. So we're going to be looking at strongly convex functions with Lipschitz gradients. Okay, and I know that the mathematical definitions might look a little bit intimidating, but a strongly convex function is basically a function that we can lower bound by some quadratic. There's some sort of lower bound on the curvature, and this lower bound on the curvature is called m, and needs to hold across the whole function. So for example, this function here, okay, is not strongly convex, and m needs to be strictly positive. Okay, so this function here is not strongly convex because the function has approximately 0 curvature here, right? And as we tend to minus infinity, the function has 0 curvature, so it's not strongly convex. Okay, so we also want a function with Lipschitz gradients, so we don't want the gradient of the function to have jumps. Okay, so we do not want things like this. Okay, in particular, if a function has Lipschitz gradients, you can also think of it as an upper bound on the curvature of the function, right? So at every point, the curvature of the function is bounded by L. Okay, this needs to be smaller than infinity. And for example, this function here is not a strongly convex function with Lipschitz gradients because of two reasons. First, because the curvature here at 0 is 0, and second, because the curvature increases arbitrarily large for large x. Okay, so if the function is totally unconstrained, then it's again not in this family of strongly convex Lipschitz gradient functions. So we define this function by SML. So M being the lower bound on the curvature of the function, and L being an upper bound on the curvature of the function, and this kappa is some sort of condition number. And our results are going to be expressed mostly in terms of this condition number kappa, which tells us how hard the function is. In general, functions that have a high kappa have regions of low curvature and regions of high curvature, and makes the optimization problem harder. Functions that have a kappa close to 1, which is the smallest it can be, because L is always bigger than M, are functions that are kind of more nicely looking and are therefore easier to optimize. Okay. Okay, as I mentioned, we're going to be looking at rate bounds defined in this way. So we want the iterates, the error of the kth iterate to be bounded by some rho k times the, this thing should be a x star, times the distance of the original iterate to the optimum. Okay, so there's a typo here. This should be x star here. Okay, so we're going to be looking at things of this kind, trying to find these rows. And so what is known for Nesterov's function, and from Nesterov's lecture on his book, we know that if we set alpha is equal to 1 over L and beta is equal to this expression here as a function of the condition number, kappa, then the rate, it proves a row of this form here. So it's an upper bound, okay? And for quadratic functions, using the kind of techniques that I'm going to be talking about here today, Lessard proves a tighter bound, okay, that in this case it's exact and it's the best you can get for quadratic functions, but just for quadratic functions, okay, and the tuning is different, and the bound is better. So this is a general bound, this is a specific bound. So that's what's known so far, and that's how the picture looks. So if we plot how the bound changes with the condition number, with log of the condition number. So this bound is generic, a little bit worse. This bound is better, but it's specific for quadratic function. And again, I want to emphasize that these things are just how exponentially fast. Maybe I should call this in row because that's, I guess, the letter I'm using. So this is just how exponentially fast the error goes to 0. Okay, so that's not the error itself. It's the speed at which the error goes to 0. Okay. So what question do you have about, if any, about the problem and the setup that we're trying to understand? And our purpose is to get something better, right? Can we get something that is as generic as Nesterov's bound, so it works for any function, but it's better than his bound? Okay, of course we cannot go beyond this line because this line is for a specific class of functions, quadratic functions, and for that specific class, which is included in our class SML, this is the best you can do for quadratic functions. You cannot beat this for quadratic functions. So the optimal generic bound should be somewhere between this line and that line. And we want to see if we can kind of push the envelope down.
Does Nesterov have lower bound also? Or?
There are lower bounds, but lower bound is, and I'm not sure if that's, maybe in the next slide we'll see. Lower bound is somewhere here, but lower bound is not achievable. Okay. But there are lower bounds, and the lower bound that Nesterov has is for any first order method. So he has a kind of a bad function that he can prove that any first order method for this bad function requires at least this many iterations and whatnot. Okay. Okay. So the way we're going to achieve this is using this theory of integral quadratic constraints. Okay. And okay, so how does this work? So these optimization schemes can be seen as a dynamical system. There's some iterates that are evolving that are a function of the previous iterate. In particular, this scheme is a first order scheme, so the iterates at time t plus 1 are some function of the iterates at time t. These optimization schemes can be interpreted as a linear system with a nonlinear feedback. For example, for Nesterov's scheme, I can think of it like this. There's a linear system here, okay, and then this y variable is input into this nonlinear function, which is the gradient of f, and tells me the next control input u. Okay, so it's a linear block and a nonlinear feedback here. Okay, and so studying the convergence of this optimization method is equivalent to studying the stability of this linear system with nonlinear feedback block. Okay, and so then the fourth thing that this framework does is kind of reduce the analysis of the closed loop system to analyzing an open loop system. Okay, now this thing sometimes people get confused here. So let me kind of go over kind of slowly, and please do interrupt me if you have any questions. Okay. So assume that we have a linear system. Okay, in this case, our Nesterov linear block. Okay, and that we probe this system with some function, and that let's assume that for any u that we input here, z of my probe satisfies. So for any u such that z for my probe satisfies some constraints c, okay, a certain property p holds. Okay, so I prove, okay, I can prove somehow that no matter what u I put here, okay, as long as z satisfies some constraint c, a certain property that is useful for me holds, and this property will be the convergence rate. Okay, and now let's probe this complex system which has a nonlinear feedback with the same probing function. Okay, if the z that I obtain here satisfies the constraint c, then p also holds. Okay, and why does p hold? Because this first part was for any u. Okay, in particular, it's also true for a u that was obtained through a nonlinear feedback. Okay, so if I can establish something like this, if I can find a probing function such that if z satisfies some constraints, then my useful property holds, then for the system with a nonlinear feedback, all I need to do is to check that this constraint c also holds, and I will get property p out of it. Okay, so that's kind of how we analyze the open loop system. So how we analyze the closed loop system using an open loop system. Okay, so what question do you have about this slide here? So this is kind of normally the most kind of confusing part of the talk. So okay, so in our case, these are going to look like this. So for generics, and this was a theorem that was established by Lessard a couple of years ago, I guess 4 years ago now. So we have a linear system, we have a linear probing function, okay, and then so these are going to be our conditions C. So if these two conditions hold, okay, so this Z, the output of my probing function satisfies some property, okay, and I'll kind of parse these two properties here. So if the output of the probing function satisfies these two properties, then these two constraints, then this property here holds. So the property is that my signal x of t converges to some fixed point x star, okay, at the rate of rho. Okay, so that's what I want to use, because that's how I want to extract my bound for Nesterov scheme. Okay, so let me parse what now these symbols mean. So u star, x star, and z star are fixed points of a sequence. So that I just have a generic sequence u, x, and z. I have a fixed point of the sequence. Okay, if I can find a row between 0 and 1, such that this inequality holds for any k for some matrix M, okay, and for this row that I found there, and if in addition this SDP is feasible, okay, which depends on the matrix A, B, C, and D, and matrix M that I need to find, a lambda that I need to find, and a P that I need to find. Okay, the P needs to be positive definite, the lambda needs to be positive. There's no restriction on M. So if I find an M, a P, a lambda, and a rho, such that this thing holds for the Z that is the output of my probing function, then I'm guaranteed that the speed at which I converge to the fixed point x star is a rate of rho. Okay? So basically the conditions I need to check are, I need to find a rho, I need to find an M, so maybe I should write what I need to find. So I need to find an M, a rho, a P, and a lambda, okay, such that these things hold. Okay, if I find such a thing, and this thing needs to hold for every k here, if I find such a thing, then I'm guaranteed the convergence rate of rho. Okay. Of course, I also need to design. Sorry, I also need to design my probing function, I guess. So I also need to design C and D. So I need to design my probing function, C and D, and then find M, rho, P, and lambda. Okay, so I need to kind of do a lot of stuff here, okay? But fortunately, some of the things were already done for us, so we don't need to, we have a good guess on some of these things to start with, okay? So let's now go through the, let's now go through the recipe with Nesterov's scheme. So we know that Nesterov's scheme can be written in this way, this standard form, and we can actually write it as a first order linear system. I introduced this extra variable zeta here just for later convenience. Okay, so, but basically, if you just ignore this part here, this two-dimensional system will define z. So I can replace y here. Okay, and you'll get exactly the same thing. Okay. So, okay, as I mentioned, okay. And now here I should make a kind of just a quick stop. So I'm treating these variables as one-dimensional. In fact, you know, I should kind of do this product, this tensor product with identity, because the variables might be n-dimensional in general. But just so I don't carry this identity everywhere, I'm just going to ignore it. Okay. So when you see like 1, it should actually be the identity matrix, and when you see beta, which is just a scalar, should be actually be minus beta times the identity. So every block is diagonal, okay, with dimension equal to dimension of my problem. Okay, I just don't want to carry these things around a lot. Okay. Okay, so we're going to define A and B in this way here. Recall that A and B are just my specification of the system in this form here for me to use the theorem. So that's my A and B. Okay, that's the A and B right here. That's good. And now we're going to use this lemma again by Lessard that already tells us what probing function we should use. So if I define a probing function in this way, okay, that depends, again, the probing function receives u and y. So if I define the probing function this way, which is a linear function of y and u, and if I define u to be the gradient of f, where f is a function that is strongly convex with Lipschitz gradients, okay, then I'm guaranteed that the first part of the property of these constraints holds for this matrix M here. Okay, so I'm told that if you choose this probing function, okay, and if u is given by this nonlinear feedback, which is our situation, then this first weird condition holds if you choose M is equal to the 0, 1, 1, 0 matrix. Okay, so we're going to go with this choice. You know, we could have tried to use other probing functions, but we went with this one because at least we already have guaranteed half of the conditions they need to hold, right? Just to kind of recall. So this part here, okay, is already kind of guaranteed. So they specify for us the probing function, the C and the D, okay, and they show that if you choose that C and D according to that linear probing function, and if you choose M like they told us 0, 1, 1, 0, then this part here is cool for any row actually. It doesn't matter what the row you choose, it's actually going to be satisfied. Okay, so that's what we're going to go with. So these are linear probing function. Of course, we want to write it in a more convenient way. So the linear probing function will be written in this form here, where this thing will be our C and this thing will be our D. Okay, so now we have A, B, C, and D, right? So we have the A, B, which was basically from A, B came from basically literally Nesterov scheme. Now we have this part here also kind of established by this lemma from Lessard that tells us a good probing function that he has used to prove bounds on other algorithms. So we just go with that. We still need to specify these variables here, so we'll keep going along. Okay. Okay. So these are C and D, as I mentioned. Again, same thing here. This thing, every one of these entries should actually be some scalar times the identity. Okay. So these are all block diagonal matrices. Okay. Now the next thing we need to do is to try to find a rho, a p, and a lambda such that this thing here is satisfied. Now we have A and B that came from Nesterov's scheme. We have C and D that came from our probing function, and M that for that probing function satisfies the first constraint. Now we need to find what is smallest row, of course we want to find a small row, right? We want to find what is the smallest row for which we can find a positive definite matrix P and a strictly positive definite matrix P and a positive constant lambda such that this inequality here holds, where this in here just said that all the eigenvalues of this matrix here need to be negative. Okay, not non-positive, I guess, non-positive. Okay, so that's what the last thing we need to do. And you can see that there's all of the things that we've done here could be easily done for many algorithms, for gradient descent, we have done it for ADMM in the past. We just need to follow the recipe. Normally A and B are easy to find. The probing function, at least in the past, we've had success just using the one that Lessard suggests. And so then the whole problem boils down to kind of enforcing this constraint here. Okay, that's the hard part of the problem. Okay, so we call this thing the IQC matrix. Okay, and so these are what we know so far. We have the A and the B that, as I mentioned, come directly from Nesterov's scheme. We have C and D that come from our probing function, and M for which the first part of the constraints hold. Okay, and now we just need to find the rest. Okay, again, just to mention that there should be like tensor product I multiplied everywhere, but this thing here being negative definite is equivalent to this thing here being negative definite, because this tensor product with identity does not change the eigenvalues in a significant way. Okay. Okay, so we can actually, even before we do some math, we can numerically find these rho and these p. So if we fix rho, let's say I want to guess a certain rho. I guess maybe that rho is equal to 0.5 works for certain choice of parameters. Right? I need to do this thing for some choice of parameters. So I fix some alpha. So I fix some step size. I fix some momentum. I fix some L and M, some upper and lower bound of my curvature. So everything is now just numbers. Okay, the A, B, C, D matrices are just numbers, and M is already only numbers. And then I guess some rho. I'm going to guess rho is equal to 0.5 for this choice of algorithm parameters, and for this kind of choice of bounds on the curvature of my function. Okay, and so if I make these choices, then this matrix here is linear in P and lambda. Okay, so this thing can be solved by standard convex optimization methods. We can numerically solve it, and we can check whether it's feasible or not feasible. So if it is feasible, then we know that for this choice of alpha, beta, L, and M, we know that we have at least a convergence rate of 0.5. And then we can use, by noticing that the eigenvalues of this matrix here are monotonic, change monotonically with rho. Okay, we can use bisections to find the best possible, smallest possible rho. So if the rho is feasible, then I try to choose a rho that is smaller. If it becomes unfeasible, we try to choose a rho that is a bit larger, and we use bisections to find the best possible rho that satisfy this constraint here. And we can do that numerically, and that's what we get. So this is the general bound that Nesterov gives us, that we saw initially. This thing is the bound that Lessard computed for quadratic functions that cannot be improved. And this orange curve is the bound that you get if you use IQC framework, and you find the best rho that you can extract for our choice of probing function. Okay, and you see that it's a generic bound on any function, so you can get it for any L and M. Okay, you can get such a thing. Okay, in this case, it turns out that it only depends on the condition number, and it's actually better. Now the question is, how do we extract? And this was obtained, as I said, you need to make a choice for it to obtain the curve numerically. You need to get a choice of alpha, beta, M, and L. So what we do is that we fix L. We define M from kappa, because kappa is equal to L over M. So fix L is equal to 1. For any kappa here, we figure out what M is, which is just 1 over that. And then we choose alpha and beta according to these tuning rules that were suggested by Nesterov's scheme. So Nesterov's scheme Nesterov's bound was proven for this choice of parameters, so we make this choice of parameters. So now everything is a function of kappa, and then we just fix kappa for every point here on the x-axis, and we solve this little optimization problem, use a bisection, and we get a point, and we get this curve. So the curve is actually better than Nesterov's curve, so it means that the IQC framework can actually get better bounds than the known bounds for Nesterov's scheme. We already saw these two equations in the past. Now the question is that this thing was just numeric, and there's no, we didn't get any closed form expression for this stuff. So how do we do it? And so now that gets me into the kind of second part of the talk. So the first part is, okay, we need to apply this IQC framework for Nesterov's scheme. How do we do it? We kind of follow the recipe, nothing really fancy. We reduce the problem of finding the bound on the convergence rate to solving an SDP that we first solved numerically, just to kind of see if we could actually get something useful, which we can. And now the question is, can we actually solve this SDP in closed form so that we can get a closed form expression for this thing here? Okay. Okay, so we can actually get an explicit bound from this IQC framework by solving this SDP explicitly. And as I mentioned, this thing can be applied to other methods, and we've had some success in the past. We've also used it to get the currently best known bound for ADMM for strongly convex functions was also obtained by us a couple of years ago using the same technique. And it turns out that for ADMM algorithm, we proved that you actually can achieve the best possible rate among all first-order methods. So the Nesterov provides a bound on any first-order method, and ADMM actually achieves that bound. So Nesterov does not achieve that bound, but ADMM does, if everything is properly tuned. You also get tuning rules from this technique. Okay. Okay. So how does this IQC matrix look like? Well, it's a 4x4 matrix. Okay, but the dependency of the entries with our parameters L, beta, M, lambda, and also don't forget that we also need to find this P. So P is some positive definite matrix that we need to find. So if we parameterize P by AB, it needs to be symmetric, of course. By the entries of P, then the entries of this matrix look like this, so they don't look simple. And so if you just try to, okay, this is a 4x4 matrix. The eigenvalues have a closed form expression because they're the roots of a fourth-order polynomial. So you just plug in everything into a symbolic solver and you say compute the eigenvalues. It's just not going to fly. Okay, it just chokes. So the direct approach does not really work because the expressions are very complicated. Okay, although in the end we just want to compute the spectrum of a 4x4 matrix. Okay, but it's not just that. We want to compute the spectrum of 4x4 matrix, but then you want to guarantee that the spectrum is negative, and you want to find A, B, C, D, and F such that the spectrum of P is positive, and that the spectrum of this thing is negative, and then you want to change rho to make it as small as possible, such that these two properties hold, that this thing is negative definite, this thing is positive definite, and that lambda is bigger than 0. So it's not just computing the spectrum. You need to compute the spectrum and then kind of optimize the spectrum while keeping in mind some constraints. Okay, so it's a bit more complicated than that. Okay, so here's our approach, and this is literally how we did it. So it took us about a year and a half. So we basically start from, and I'm not sure this is the best approach, but that's the approach I know it works, and that's the approach we also did for ADMM. You need to be patient, and try a lot of stuff. So we first try to fix as many variables as we can, and then we try to, with a lot of variables fixed, we try to guess, and we run some numerical simulations, try to guess relations among the entries of these matrices. We get some guesses, and then we try to enforce those guesses mathematically and see what follows if we enforce those assumptions. And then we get some equations in the end, and then we back substitute, and then we check the eigenvalues to see if they satisfy the properties that we want. Okay, and if they do, then we make another variable free that was fixed, and then we repeat the procedure. Okay. And as I mentioned, we get these numerical solutions for different values of alpha, beta, m, and l, and we do it using CVX in MATLAB and bisections to find the best possible row that makes this IQC matrix negative definite and this SDP feasible. Okay, and then we try to find patterns in the entries of these matrices, and then, as I said, we can enforce the patterns, and we get some equation and we back substitute. Okay, so here's just an example. So for example, if we have alpha free, so alpha is kind of varying, and we force beta is equal to 1, and we make L is equal to 1, which I actually didn't write here. We make L is equal to 1, beta is equal to 1, so M is also free, and then we numerically solve the IQC matrix. We numerically solve the SDP associated with the IQC matrix. We observe numerically that these relations seem to hold. So if we make a plot of, and the reason why we just guessed these, okay, we guessed that it to be something like this, square root kind of things. So if you numerically plot rho versus this quantity here, it follows a linear relation. So we guess, well, this seems to be true. We also observed that in general E was always very close to 0. E being one of the entries of this P matrix that needs to be positive definite. Okay, so this thing was in general always 0, and this D and B follow this relation here. Okay, actually P is right here. So basically, we kind of numerically observe a relation between rho, M, and alpha of this form, and we observe some relation between the entries of P like this. And now, based on these guesses, we kind of substitute that, we enforce those into our matrices, which simplify the expressions substantially, that make the spectrum much easier to compute, and then we check whether the eigenvalues satisfy the right properties. Okay. So, what other things have we observed in general? So this was for a specific setting where alpha is free and beta is equal to 1. So, what we observe in general. We observed that the minors of the matrix are in general 0. So if I have the IQC matrix, this 4x4 matrix, and I delete the first row and the first column, and I compute the determinant, the determinant is 0. And if I do that, if I eliminate the second row and the second column, and I compute the determinant of the 3x3 matrix, the determinant is 0. And same thing if I do that for all of these 1, 2, 3, 4 columns. Okay, 1, 2, 3, 4 rows. So that's observed numerically. So in all experiments that we did, we observed this in here. So we enforce that. Okay, so we get 3 equations, and then what we do is that we use a symbolic tool to see what we can get by enforcing the determinant to be 0. There's 3x3 matrix. The determinant also has a relatively complicated expression, but it's much simpler than computing the spectrum and the roots of a 4th degree polynomial. So it's just some sort of kind of polynomial equation to get out of here, and we try to use a symbolic solver to get some relations out of it. Okay, and then for every one of these equations, every time we get some equation, we try to solve for one of the variables in the equation. So this equation will involve many variables, A, B, C, D, F, whatever. We try to solve for one of the variables, one that is simplest to solve for. We get the relation, we back substitute into the full 4x4 matrix, and we simplify. And then we enforce some other minor equation. We try to solve for one of the variables. We get an expression. We back substitute into the IQC matrix. We simplify, and we repeat the procedure until it gets simple enough that we can do math. So that's one set of constraints that we have, that all these diagonal minors are 0. The other one comes from this applying Schur complement. So we know that the whole IQC matrix needs to be negative semi-definite. So the minus of that matrix is to be positive semi-definite, and there's a condition for positive semi-definiteness for matrices given by the Schur complement, which is that this matrix, if the matrix X has this form here, then this thing is positive semi-definite if and only if this matrix here is positive semi-definite. So this should be like a kind of curve inequality here, and A, B, and C satisfy this relation here, and C and B satisfy the relation here, where this small g means pseudo-inverse. So these matrices might not be invertible. So okay, so we also enforce that on our full matrix because we know that needs to satisfy, and we get three relations that this needs to be positive definite, this needs to be positive definite, and this needs to be equal to 0. And we get one equation from here that we solve, and we get some more constraints that we kind of then back substitute into the IQC matrix. And these two things here, we kind of just check at the end that they are satisfied, and they are satisfied in the end, okay, after we make all these back substitutions, okay? So this is the general procedure that we follow. So it shows alpha is equal to 1 over L, which we can then choose L is equal to 1 by normalization arguments. Okay, so we choose alpha is equal to 1 over L is equal to 1, kappa is equal to 1 over M. So kappa is in general L over M, but because L is equal to 1, we got kappa is equal to 1 over M. And then all these variables are free. So M, beta, alpha, P, which is this 3 by 3 matrix that has A, B, C, D, E, F variables there. And rho is free. So there's 10 free variables in total. We generate numerical solutions. We guess patterns. We substitute in the IQC matrix. We solve the minor equations. So delete one row and one column, get the determinant, try to solve for some variable, back substitute. We do that for all of the 4 diagonal minors. We apply the shared complement condition. We get one more expression. We back substitute. We finally get some matrix that is actually manageable because we've eliminated a lot of free variables. We compute the spectrum of that matrix, and then we check that all the conditions that we impose throughout this in here are satisfied. Okay, so that's basically the idea behind the proof. I'm not going to go through the math. It's in the paper. The expressions look horrible, but we didn't actually do the math by hand. Okay, so the procedure is, again, this is very mechanical. So you just follow the recipe. You follow this recipe here, and you just use Mathematica or some other symbolic solver, and things work. Okay, so that's it. So that's the theorem we were able to prove. So if for any function in this family of strongly convex functions with Lipschitz gradients, if we choose alpha is equal to 1 over L, then the convergence rate of Nesterov's scheme is bounded by rho, where rho is given by this expression here, and beta should be chosen in this way here. So we don't. So this choice was just a guess. This tuning rule was extracted from our IQC procedure. This thing was just a guess. We couldn't, if we try to put alpha free and we try to go through the procedure with alpha and beta free, there's just too many variables, and we couldn't really. The symbolic solver could not make sense of the equation. So we had to fix this. So these tuning rules, I guess, 1 over L, and then the rest was derived from following this procedure. Okay. Okay, now this expression here that looks very complicated actually is numerically very close to Nesterov's choice. So Nesterov proposes square root of kappa minus 1 divided by square root of kappa plus 1. So we propose this, which is substantially more complicated. So Nesterov also said that we should choose 1 over L. But numerically, these things are very, 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 they're not the same, but they're very, very close. Okay, which is interesting. But the rate is much better, right? So this is the rate that we get, and that's what's currently known. So this is the general bound obtained by Nesterov. This thing is the best bound on any first-order scheme that Nesterov's scheme cannot reach, but that we have proven a couple of years ago that ADMM actually can reach this thing here. This thing is the best bound for quadratics that you can get for Nesterov, and you can prove you cannot get better than this. So this is the fundamental lower bound on the convergence rate of Nesterov's scheme. So Nesterov also has a bound for quadratic functions, which is actually not optimal. So the Lessard's bound for quadratics is the best you can get for Nesterov's scheme. Nesterov also computed the bound for the specific case of quadratics, which is slightly worse. So these are not generic bounds, these are specific bounds. Our bound is here, so it's the best currently known generic bound for Nesterov's scheme for strong convex function, okay? And it is substantially better than Nesterov's bound. Okay, and it's closed form. It has a closed form expression with closed form tuning rules. Okay. Okay. So let me pause here. So what questions do you guys have? Yes.
So you just mentioned that your choice of beta is very similar to Nesterov.
Yes.
But in fact, your role is much better.
Yes,
And
yes.
do you run some on real data to show that your convergence rate indeed better?
I didn't do experiment because I have a proof, so I didn't have to.
Yeah, but Nesterov's method seems to work on the real data, so I'm curious about
Right.
Your choice.
Right. So the choice is right. That's a good question. So here's the situation. So one thing is what you observe empirically. The thing are the proofs, right? So our tuning rule is very very close to Nesterov's tuning rule. So in practice, using ours or theirs doesn't make any difference. Ours or theirs are probably going to be giving you a bound, an actual rate bound that is better than theirs and better than ours. Okay. So the actual empirical bound that you get from choosing those tuning rules is probably going to be better in both things. But now, from an analysis point of view, right? One thing is what you observe experimentally. The other thing is what you can prove. From an analysis point of view, Nesterov was only able to prove this bound using a particular tuning rule. For a very close tuning rule, we were able to prove a better bound, right? So you see the difference between, right? So you might guess some tuning rule that performs really really well in practice, but then you might not be able to prove that what you're observing, right? You might be able to prove something that is worse than what you're observing, and that's the situation. But you're correct. So if I use my tuning rule or Nesterov's tuning rule, there's not going to be any difference because these things are virtually because we're choosing the alpha exactly the same way, and the beta is virtually indistinguishable. Okay, so we are not going to see any difference between our choice and their choice. But it turns out that our choice is the one that allows us to carry the proof. So if we make his choice, the proof doesn't follow. Okay, the math doesn't follow. Okay, okay.
Thank you.
Good. But that's an important question, right? Okay. Any other questions? Okay. Good. So another thing that we were interested in is okay. So this is one bound that we can get from this IQC framework. Can we get a better bound? So one thing that we did in the previous work on ADMM is that we not only we obtained a bound from this IQC framework, but we were actually able to prove that you cannot get a better bound from the IQC framework, and that was because if we can achieve the fundamental lower bound on any first order scheme, then you obviously cannot get something better from any framework, not just the IQC framework. But in this case, we are still far. We're still far from obviously from the fundamental bound, but we're still away from the best quadratic bound. Okay, so the question is, okay, is this thing the best bound that you can get from IQC framework? Maybe it's possible to get something slightly better, right? So what we did is that we made more numerical experiments where instead of choosing alpha and beta like we chose other alpha and betas, and we can numerically see that there's actually other bounds that one could extract from this IQC framework that are better than the one we have. And these are just numerical experiments. For example, so if we choose alpha is equal to 1 over L like we chose, and beta just like ours, this complicated expression, then we get this curve here, this yellow curve. But if we choose, for example, alpha given by this expression here, and beta is equal to ours, okay, and we run these numerical experiments, we actually get the better bound. And if we choose alpha and beta given by the tuning rules for the quadratic case that less are proved, we get better bounds even. Okay, so from the IQC framework you can actually push the bound a little bit more, but we were not able to prove. So if we make a different choice of alpha and beta, again the math does not follow. Okay, so the IQC framework, we've not squeezed all the juice we can from this IQC framework, but at this point is not that simple. It's not that simple. Okay. So maybe we need to choose another probing function, for example. So maybe our choice of probing function already kind of limit things on the onset. Okay. Okay. So to finish up, so a few open problems. So the first one is, what is the best bound that we can get from this IQC framework for Nesterov scheme? This is still an open problem. We know that there are better bounds. We just don't have an analytic expression for them. So I kind of invite you to try to solve this problem by, again, trial and error and smart guess and whatnot. The other interesting open problem is what is actually the best possible bound we can get for Nesterov scheme, right? So and in particular, is it the case that with a special tuning rule we can achieve a bound for a generic function that matches the bound for the quadratic functions. Or said in other words, are quadratic functions the worst functions for Nesterov scheme, or are some functions that are for Nesterov scheme worse than quadratics, right? For example, for ADMM, the worst possible function you can give it is a quadratic. So it's enough to make the algorithm as slow as possible. It's enough to give it a quadratic with a properly chosen curvature. Okay. For Nesterov scheme, it's not clear whether that's the case. It's not clear if the worst functions inside the family of strongly convex functions are quadratic functions. Okay. So maybe they are. Okay. And if that's the case, it should be possible to move this line all the way here, either with a different proof technique or with this IKZ framework, but maybe they're not. So maybe there are some function that is not quadratic, that is strongly convex, that is somewhere in between this line and that line, okay? And that's actually the worst thing you can give for Nesterov scheme, and using some other proof technique, you can actually match that lower bound. So that's also currently not known. And that's it. So I'll take questions if there are any other questions. Yes.
This brings up the memories of the four-color theorem proof, when the whole math world was outraged because it involved a lot of computer search and help from computers. One thing, because there's too much help from software systems here. One thing that it doesn't show is really why the intuition behind Nesterov's method.
Right.
Nesterov did this so many years ago. He had no computers. What is the logic? Why does it work so well?
Right.
So one thing that would be potentially interesting, and maybe more interesting than just trying to tweak the bounds and improve them, is to see that some of the conditions you got, like E being equal to 0, what do they translate into when you go back to the original method? What do they mean in terms of the actual algorithm and the choices of the parameters?
That's a good point, yeah.
Just to get a better feeling of what is really going on with the algorithm.
Right. I do know that there's some recent papers that have some. I mean, I read a paper recently. I forgot who actually wrote it, but I can send you an email. If you send me an email, remind me. I'll send you the paper. You have a very nice geometrical interpretation for Nesterov's scheme and why it's faster to converge.
But how does it relate to this?
No, yeah, exactly. It's not related to this method. Yes, it is not related.
But you could
yes, we could try. Yes, we could try. We could try. I think it's going to be a bit.
Physics approach that I know of. It was more of an approach from physics. Right. Maybe that's a different.
Well, the paper that I mentioned is very simple. Like they have a very simple geometrical interpretation. You can just draw a few circles, and you can see why Nesterov's scheme converges faster than. It's actually not Nesterov exactly. It's a kind of a quasi Nesterov scheme, but just the intuition is there. And it's very easy to read paper. It's very, very, very well written and crisp.
But can it help with getting?
No, because they just do a total, completely geometrical interpretation of the whole method.
Can help with your
not with these. I mean, with these, it might be possible. I mean, it might be. You're right. I mean, we didn't think about that. So it might be possible to kind of reverse engineer these conditions and see what do actually mean for the algorithm. We didn't think about that at all. So I will try to think about that a bit more. You're right. I mean, in the end of the day, the expressions are so they are hard to get, but once you get them, they're not that long. So if you go to the paper, which is on my web page and also on archive, you have all the expressions there, and you can substitute and you can check that everything checks. It's just to get expressions, we just don't do the math by hand.
No, but I mean
right.
the conditions you
you're right.
identified, they're very straightforward.
Yeah.
What do they really imply?
Yeah,
if you go
that's a good point. I mean, we didn't even think about that. We were just tired of all this computation. We just want to kind of wrap it up. But that's a good point. Yes.
So the Lasat's theorem with the fixed points and convergence. So that's an if statement, right? There's no converse to that statement.
I don't think so. No, it's like if some conditions hold, then you get a bound on the rate.
But if you had a converse, would that be helpful in constructing counterexamples and showing?
That's a good point. Right, that's a very good point. What you can do, there's no converse, but you can still try to use it as some sort of guess of bad functions, right? So the theorem only works in one way. But what you can do is, okay, let me try to choose some functions for which the theorem does not follow, and let's see if that's a bad function in practice. So it's not you don't have a mathematical reason for it to do that, but you can definitely try to do it. And that's actually something that Lessard in his paper actually suggests, that one could use this IQC framework to design best functions by seeing what functions make the theorem break. But it's just there's so many of them that is not. I mean, yeah. So we couldn't get something out of it. We thought about that. That's something we actually thought about, but we couldn't really get it. Yeah. But that's a good point. I think you had a question.
Oh, yeah. I'm curious about this IQC framework able to analyze something like the stochastic gradient method.
Right. That's something that we're currently also thinking about. It might be doable. What you need to do is that you prove things in expectation, and then you use some sort of concentration bounds, right? So basically, you have these matrices for which you need to compute the spectrum, right? Now, what's going to happen in a stochastic setting is that these matrices are going to be stochastic themselves, okay? And then you want to show something like with high probability the spectrum is something, right? And so what you're normally going to do is you're going to show that in expectation the spectrum is something, and then use some concentration bounds to get a handle on it. I've never seen people do it. That's again something that Lessard suggested is in the end.
I think he's doing it. We had some people give talks about Lessard's recent, maybe preliminary results, but I think people in his group are working on it.
I know that because he mentioned that in his paper. He mentioned a few things that have not been done. One of the things was the fact that, in general, people do not get explicit formulas from this in here. So as far as I know, there's only 3 non-trivial results on getting explicit bounds from this IQC framework. 2 of them are from us, one for ADMM and one from Nesterov. And he recently published a paper on what he called a triple moment method, for which he also gets closed form expression from this IQC framework. But the triple moment method is something that he cooked up. It is kind of a momentum kind of method, but it's not exactly like Nesterov. And for that method, you can achieve this bound here. So you can get to the green bound. So his triple moment method achieves this bound here. Now it's not as good as ADMM and our bound for ADMM, but still it's interesting that you can achieve the best bound you can achieve the best bound for quadratic function for Nesterov's method. The method is kind of very similar to Nesterov, but it's not exact Nesterov. So if you just Google triple moment method Lessard, you'll see his paper. So there's only 3, as far as I know, there's only 3 examples of analyzing non-trivial algorithms that lead to explicit bounds, and then that's what we focus first. But there are other things that are still open, stochastic versions of these things, adaptive versions. So when you have adaptive parameters, trying to get bad functions out of the framework. So just a few ideas, and all of these ideas he mentions it in the end of his paper. Things that would be interesting to try. We just thought that going for explicitness first would be more interesting. But that's a good point. Yeah. Right. Okay. Thank you.